Hello, everybody, for today's Early Career Scientist seminars. We have 3 great talks ahead, and our first talk today will be from Marissa Dattler. She is a candidate at the University of Maryland and a research assistant at the Cryosphere Science Lab at NASA Goddard Space Flight Center. And her research currently focuses on airborne and satellite remote sensing of ice sheet and surface properties, including firn compaction and surface melt. And yeah, welcome, Marissa, and yeah, I'm happy for your talk. Looking forward for your talk.
All right, thank you so much. I'll just share my screen, I guess. Okay, can you guys see it?
Yes, but we are, yeah, now it looks good.
Okay, all right, good. So today I'm going to be talking about a first look at airborne-derived firn compaction on ice sheets using repeat flight tracks from Operation Icebridge. And I work with Brooke Medley and Max Stevens at NASA Goddard, and I'm a PhD candidate. And so as snow accumulates onto the surface of an ice sheet and compacts and densifies, forming firn and glacial ice eventually, density generally increases with depth, and the rates of compaction and densification depend on things like accumulation rate, snow density, snow temperature. And as layers compact, they decrease in thickness and increase in density. And this results in a reduction in surface height in the absence of accumulation. And that's especially important for satellite laser and radar altimeters like CryoSat-2 and ICESat-2, which detect surface elevation changes at various spatial and temporal resolutions. So those are CryoSat-2 and ICESat-2 pictured here. And as you can see in this firn column, as you move forward with time, I'm just going to put my laser pointer on. As you see in the firn column in time 0, to time 1, it reduces in height, and these height changes are notable for altimetry, and they result in it affects how you calculate mass changes, which is important, of course, for mass balance of ice sheets from altimetry. And so this is impacted by firn compaction, but firn compaction is only available from localized measurements from a handful of sites on Greenland and Antarctica. And these sites really aren't representative ice sheet wide. And so what's used instead is firn modeling. Firn models are used to calculate mass changes from volume changes from altimetry. And the compaction within these firn models remains difficult to evaluate, seeing as there's so few sites that are available in order to validate them. And that's where kind of NASA Operation Icebridge's snow radar comes into play. So Operation Icebridge is, or was a decade-long airborne campaign. And the data we're going to be talking about today is over the Greenland and Antarctic ice sheets. And so it images the upper 0 to 25 upper 25 meters of snow and firn stratigraphy. And so this is an echogram, a plot of a long track, the 25 kilometers along track, where you can see the firn stratigraphy being resolved by the instrument. And you can see this orange line here, which is a manually traced layer. And so each of these layers are individually isochronal, meaning that they were all formed at one time as the rest of the layer. And so this gives you information about accumulation rate. So where you have shallower areas where the tracked layer is, there's less accumulation. And where you have deeper track layers, there's greater accumulation over the same period of time as they're isochronal. And so this is useful in manually detecting accumulation rates, which has been done in a number of studies. Super useful, but taking this one step further, we can actually look at repeat tracks. So not just one image for a specific location. We consider a repeat track of a flight that is overflown a second or third or potentially more times. And we can see that plotted up here in terms of Greenland on the left and Antarctica on the right. Greenland has more repeat tracks for sure, but there are some in Antarctica as well. So this allows us to think about compaction, which is a time-varying variable. And so if we consider one trace or one vertical cross-section of the radar echogram, we can plot up what the stratigraphy looks like. So this is at the surface at 0, and then down with depth, which is down with radar travel time, which is a proxy for depth. You can see the variations in power return, which represent these layers. So this is from a 2016 trace. If we compare this to a 2011 trace, so a trace that was taken just 5 years previously to the 2016 trace at the same location, we could try to line up the layers to see if we can get accumulation and compaction. So the way we do that is essentially taking the older trace, the 2011 trace, and moving it downward over the newer trace to try to see where they line up, all at the same time compacting it slightly, vertically straining it along the depth axis in order to get a lowest root mean square error, the best match between these two traces, to see where the layers actually line up with one another. And so that gives you information like new snow accumulation as well as compacted snow, so two variables. So essentially we shifted the stratigraphy downward to get new snow accumulation, and then we at the same time we tried vertically straining it to get firn compaction as well. And so if we fixate just on here where the layers overlap each other, we plot that up along a 5-kilometer segment, we can see that we're actually able to plot this not just in one spot, but multiple spots along track. We can see that we're able to line up these traces and get an accumulation rate and compaction rate. So I kind of breezed over how we vertically strained, how we calculated a vertical compaction rate, but we do it with various compaction profiles. So these are the different colored lines. So with depth, they vary. So there's generally greater compaction near the surface and lesser compaction with depth. And we just input a lookup table of a variety of different compaction profiles that look something like this, like large conglomeration of black lines. And then we choose which compaction profile creates the best, the lowest root mean squared error between these two. And we select that line. And so that's the red line here. And we can see that the compaction near the surface is 0.1, meaning that the near surface layers decrease in thickness by about 10% and lower as you go down with depth. And if we focus now on the top of this lined up layers at the interface between the newer accumulation and the older, we can plot that on this 5-kilometer echogram. So this 5-kilometer echogram on top is from the newer traces. It's from 2016. And then below it is from 2011. So essentially, if we took the 2011 echogram and you squeezed it variably and placed it exactly on top, right where this red line ends, that would be the layers that correspond to one another, and anything above it would be the new snow accumulation that's since fallen between the two periods of time. Okay, so this is an example from Thwaites Glacier, and we can see that we have a varying accumulation rate over the course of this segment, with generally higher accumulations very slightly, where this layer is a little bit deeper, although it's fairly flat, and a little bit lower accumulations where this layer is shallower. So that would make sense given how we calculate accumulation. And We can also see that compaction varies as well, although there is noise in this what we're looking at, but we're getting some idea of what the compaction rate is. And we also look at compaction in the interior of Greenland as well for a specific 5-kilometer segment. And we have this, again, red line, which is above which is the newer snow accumulation, below which is the matched up layers. And then we can plot up accumulation as well as compaction as well. So looking at that across the Greenland ice sheet, we can, the interior of the Greenland ice sheet really, but this is what I've plotted up so far in terms of Operation Icebridge data. And so we have on the left is what I call OIB accumulation. This is the new snow accumulation value that we've calculated, and then I directly compare to MERIT 2's precipitation minus evaporation from the corresponding years that these refer to, and plot that up, and we can see that these are very related. The R squared is 0.8, so that means that it likely means that our new snow accumulation calculations are pretty robust, but it also means that MERIT 2 P-E also might be, it might be a good approximation for accumulation in this situation. So both kind of interesting things. And then also when we compare OIB accumulation to the compaction rate that we calculated, we can start to see that we're having similar patterns in accumulation as compaction. And that would make sense because greater amounts of accumulation are associated with lower density snow, which compacts faster. And also greater amounts of accumulation are related to thicker layers, which result in greater overburden pressure and greater compaction. So kind of something that we would expect to see so far in our very preliminary plots of these. And moving forward, there's more work we need to do with this. We need to consider compaction profiles that are more realistic. So before we were just doing like kind of automatically generated 2-slope model, but now what we want to do is work with Heron and Langway models where we input things like initial snow density and accumulation and surface temperature in order to model these profiles, compaction profiles, and use those compaction profiles in order to match up our traces. So in conclusion, this will provide key validation for firn densification models that are used in ice mass change calculations from satellite altimetry, which is very exciting. And we also have steps to go in terms of implementing the Heron and Langway compaction profiles, and then also identifying, regions and depths where these layers aren't necessarily this beautiful and succinct, easy to calculate. Sometimes there's a few layers and then it's kind of totally unclear, and then there's a layer near the bottom, and so it's not always this simple, but as I kind of presented, but yeah, kind of sorting through the files and seeing what we can actually use, and then running this process on all the files that we can use for the Greenland and Antarctic repeat flights. And then one last thing, I just wanted to give a little bit of a shout out to a paper that I just published a couple months ago, and it was creating a physics-based Antarctic melt detection technique by combining AMSR2 along with radiative transfer modeling and in conjunction with firn modeling. So what I did there was I plotted up on the bottom left-hand corner the brightness temperature, which is what you get from AMSR2, and I modeled what the brightness temperature would be if the snow and firn were always dry throughout the year. So essentially you can see over the austral wintertime periods, the austral summertime periods, there's these elevation and brightness temperature. And so basically we were flagging melt days by using this physics-based technique that instead of more statistical techniques, which just take averages, we instead actually model the brightness temperature using radiative transfer modeling and firn modeling. And then we also, on the right, we did this for the Larsen C ice shelf. In the bottom left is a specific location on the Larsen C ice shelf, and then on the right is over the entire Larsen C ice shelf. And from both the hybrid method, which is the physics-based method that I present here, and then also a few other statistically based methods that we were comparing to. So if you're interested in that, of course, feel free to check that out. Thank you.
Thank you very much for the very interesting talk. I would have many questions to it, but as always, we have questions in the end of our seminar. So yeah, I just directly give first the word to our next speaker, and yeah, we come back later to this. So yeah, our next speaker is Laura Dietrich, and she is a postdoctoral researcher at Universityof Bergen in Norway, and she both measures and models how climate signals form in the surface snow through interaction with the atmosphere. And in 2022, Laura was part of a team that sampled the first ever in situ water vapor isotope profiles in the air up to 1,500 meters above the Greenland Ice Sheet. And yeah, Laura's research supports a new, more detailed climate interpretation of water isotope records from ice cores. And yeah, this is what we are going to hear about.
Yes, thank you. Do you see my screen correctly, or is it?
Yes, we see it well.
Okay, let me just get the correct pointer here. Okay. Okay, I suppose that many, if not all of you, have heard of ice core records before. So these are usually drilled in Greenland or Antarctica, and we use them for paleoclimate archives. And usually the concept of ice cores is very often in, like, let's say, documentaries and television, for example, explained by these very distinct volcanic ash layer lines. And then you hear the moderator saying, there's a volcanic ash layer and scientists can tell about the past climate based on these. But in fact, most parts of ice cores look more like this, like it's bare ice, and you can hardly see anything else in it with your bare eye. But I would like to explain or shortly think a bit together with you about, well, if there's only pure ice, how can the pure water ice, the pure ice, record the climate? And to bring us all on board, this is due to different water-stable isotopologues that the ice consists of, and everyone just calls them water-stable isotopes. So I will also continue doing this. And what we have is, of course, the regular water, H2-16O, but then there are also various heavier isotopes that differ in either the hydrogen atom or in the oxygen atom. And then the vast majority of water in the Earth system consists of regular water. And then just this very small fraction of 0.3% approximately are these heavy water isotopes. Nonetheless, these are the ones that will tell us about climate changes or climate variability maybe also. And that is because of something that we call isotopic fractionation. So if you would picture a water body, and let's say, for example, the ocean, and the ocean has then a certain isotopic composition. So here in this concept, the red ones are heavy isotopes and the yellow ones are light isotopes. And if now the ocean evaporates, then due to their chemical bindings, it is mostly the light isotopes that go into the vapor state, so that evaporate, while the heavier isotopes are left behind in the ocean. And this process of, although the source is the ocean, the vapor will have another isotopic composition, is called fractionation. So basically the separation or two different states of isotopic composition from the same source. And if we now say that we define the isotopic composition of the ocean as 0, and then negative values mean that something is relative, like compared to the ocean, has relatively less heavy isotopes. Then if we have evaporation of the ocean, the vapor that results from the ocean has negative values. So we call this depleted in isotopes. And then if this vapor now moves from the evaporation source region, for example, towards the poles, it cools down. And therefore, well, if vapor cools down and has to fall out with precipitation or condensation is happening. And here the same kicks in again. As soon as there's precipitation, the heavier isotopes tend to fall out, while the light isotopes stay like preferentially in the vapor phase. And therefore, the further this goes towards the pole, the more step-by-step depletion you have from precipitation. And in the end, if it arrives, for example, above the Greenland ice sheet, it has quite a depleted value in the vapor, but then also resulting in depleted values in the precipitation that falls just on the surface. And the exact value of how depleted this is, or like the isotopic composition of the just freshly deposited surface snow, depends again on how much has it been raining on the way that the vapor made. The more precipitation fell out, the more depleted this value will be, or the more negative this value will be. And then generally speaking, we say that in colder climates, we have more depletion. So in colder climates, these values should be lower. And then, as you know, an ice sheet consists just of many layers of individual precipitation events on top of each other that accumulate. And the so far general interpretation has been, well, the precipitation takes the isotopic fingerprint basically of the atmosphere and brings it down layer by layer. And if you now drill an ice core here, then you would get something like a time series of the isotopic fingerprint for each climate. However, this general assumption that is usually used to interpret ice cores is neglecting one big part, which is, of course, of course, the snow, when it falls to the surface, is still exposed to the atmosphere for quite a long while, and a lot of processes happening there, and these we call post-depositional processes. And post-depositional is just basically a smart word for all the processes that happen after the snow falls to the ground. And these post-depositional processes can impact the isotopic composition of the snow while still being on top. One such a process could be, for example, sublimation of snow, which is like the evaporation of snow. And there's a large community focusing on how these post-depositional processes are impacting the isotopes before they're imprinted into the ice. And one of these projects I was part of as a PhD, which is the SNOISO project, led by Hans Christian Steen Larsen, who was also my supervisor during the PhD. And just a quick fun fact, we are not the only one, it appears, that are interested in post-depositional processes, but also the Crown Prince of Norway, Crown Prince Haakon. And he even ended up helping out with some of the measurements for the project. So very important stuff we are doing. Because what did we do? We went to the Greenland Ice Sheet in order to measure how these, at the surface, these post-depositional processes impact the isotopes. And of course, we didn't go here at the edge, but we went where ice cores are actually drilled, so on top of the Greenland Ice Sheet. And more specifically, we were in the drilling camp of the East Greenland Ice Core Project, or ESGRIP, it's called. So there, an ice core was drilled until last year. And what we did at the surface is to take a lot of, well, different measurements that will inform about how the post-depositional processes affect the isotopes. So, for example, measurements of the vapor isotopic composition, but also of the flux, like the flux of isotopes from the snow surface into the atmosphere. Or also just surface snow isotopes in different depths, so very much at the surface or further down. And here you can see the Crown Prince again helping out a bit. Yes, and together with lots of samples from other scientists as well that were in the ESGRIP camp, I think there have been a bunch of very nice and interesting new insights into how now the isotopes in the surface snow are affected after the deposition of the snow. And now I would just like to shortly tease a few of these results that I personally have been involved in. So first, one paper that I would like to highlight led by Sonja Wahl. And this is in fact very important work because it basically gave observational evidence to one question that has been debated for decades, which is, does the process of snow sublimation fractionate the snow or not? And number one, the result is no. yes, sublimation does fractionate the surface snow, and not only this, it also significantly impacts the day-to-day variability of the surface snow in ECS. So now the second question was, and this I focused in on in a paper that I led together with the others, is okay, if we know that the surface snow is affected by these post-depositional processes, is this just something that matters a bit for the day-to-day variability, or is it also something that impacts the long-term, like the ice core timescale, so climatic timescales? And what we did in our group for this is to develop a snowpack model, the snow ESO model. And with this, basically, we can simulate how the isotopic composition would look like in an ice core. And here you can see a firn core, let's say a simulation from 1990 to 2020. And the nice about this model is that you can decide to turn off or on the impacts of surface fractionation during sublimation. So this is now the old assumption, how ice cores are generally interpreted without any fractionation during sublimation. And then if you turn this fractionation on, you get this ice core line instead. And you can already see that there's quite some impact. So results from this paper is, yes, the surface vapor exchange also matters for climatic timescales. So it will imprint basically a climate signal into ice core records. And now there is still a lot of work ongoing, but maybe I want to say stay tuned for two things that are currently in preparation. One is a paper by my colleague Ines Olivier, and she has been working a bit on reducing model uncertainties and finding the correct parameterizations. And she also does Antarctic simulations with this new ESO model. And then at the same time, I'm currently working on getting this, which is currently just an ice core for the current climate, into paleoclimate perspective. So running it basically for other paleoclimates. And then it has been already teased by Falk earlier. I was also very happy to be part of project from INSTA in Boulder in the US. And there they investigated, well, if we now know that the surface snow is impacted by the vapor above, it is interesting to see what climate signal does the vapor actually carry. So what they did is to use this fixed wing drone and shoot it up into the atmosphere above ECS up to 1,500 meters, and then took in situ atmospheric vapor samples and brought them down again. And this I also want to tease because it's very close to submission. Kevin Rosmiarek is leading a paper on the results of this atmospheric climate signal, basically in the isotopes. Yes, so that was my talk. I leave you with a short, very short summaries of the papers I touched upon, and I'm happy for questions later.
Thank you very much for your very nice presentation. Yeah. And then I also directly come to our last speaker for today. So he is Advik Eswaran, and yeah, he is a student at Princeton University, where he is interested in the intersection of paleoclimate data assimilation and glaciology. And his research focuses on combining ice core records and climate models for the purpose of past polar climate reconstruction.
Okay. Yeah, well, thank you, Falk. And I guess, yeah, here's my presentation. I'll be talking about a recent study I did, advised by Olivia Truax and TJ Fudge, on a reconstruction of 19th and 20th century Antarctic snow accumulation and its resulting impact on sea level rise. And I guess, spoiler, as you can see in the title, our main conclusion was that the impact of Antarctic snowfall and its trends on sea level rise was primarily uncertain, and that's due to uncertainty in the current proxy record in East Antarctica. And to know more, we have a paper out at GRL, published a few months ago, detailing this. And so I guess to start out, a significant amount of uncertainty surrounds the future contribution over the next century of the Antarctic ice sheet to sea level rise. And that's due to two main factors. Climate models are, of course, predicting temperatures to increase, but in response to temperatures increasing, there's two competing processes going on. First, as temperature increases, the melt of the ice sheet is, of course, projected to increase as well. However, according to the Clausius-Clapeyron relationship, snowfall should also theoretically increase with increased temperature, but over Antarctica, increased snowfall will add to the mass of the ice sheet and freeze. and thereby this will mitigate sea level rise. So you can see here on the right 2 plots of how ice discharge and surface mass balance in Antarctica are projected to change. And you can see here clearly that even though the ice discharge is projected to increase and raise sea level, the snowfall is also projected to increase, and that should lower sea level. And so there's a lot of uncertainty around this, and we really don't have very good constraints on how, if at all, snowfall is going to change in response to temperature. The climate models say, yes, it will, but we don't have great constraints on the magnitude of that change. And so to understand the future, we can look to the past and see how snowfall might have changed over Antarctica in the past, over the past century or two. And if we can understand how accumulation changed during that time period, this can hopefully help us project the contribution of Antarctica to sea level rise in the future. And so then we come to our method for reconstructing Antarctic snowfall. And we use a method called paleoclimate data simulation, which essentially allows us to combine information from both ice cores, which of course you heard from Laura on the last presentation, so both ice cores and climate models. And the way we do that is we essentially combine the temporal information from ice cores going back the past 2 centuries with the spatial information, the spatial covariance from the climate models. And so that way we can essentially produce a gridded, annually resolved reconstruction from 1801 to 2000 and fill in the gaps between the individual ice core sites. And we use about 120 Antarctic ice core records, including both accumulation records and also water isotope records, even though we're only reconstructing accumulation. And we combine this with a multi-model ensemble of 9 different CMIP-5 last millennium simulations where we randomly draw individual ensemble members. And again, the combination of the 2 ice cores and climate models is what gives us a gridded reconstruction product. And so now, before we come to our actual results, we first want to make sure, like, does our reconstruction make sense? Are we producing a skillful reconstruction? And the way we do that is we compare our reconstruction with ERA5 reanalysis for the satellite era. And we know that ERA5 is at least probably the best, this being a relative term, of course, the best reanalysis product for Antarctica over the satellite era, so since about 1980 or so. So we essentially take the correlation of our reconstruction for this time period with the ERA5 precipitation reanalysis. And we find overall that our reconstruction agrees quite well with ERA5. You can see here on the left is a plot of the correlation coefficient with ERA5. On the right is a plot of the coefficient of efficiency with ERA5. And overall, our reconstruction does well. We have high correlation values, especially in West Antarctica. And in general, our agreement is worse in East Antarctica. You can see here on the right is the actual values for the 2 regions. And in a bold number means that that correlation is statistically significant. So our reconstruction is statistically significant agreement with ERA5 over West Antarctica and Antarctica at large, but not over East Antarctica. And we'll return to that point because in general, this is something that makes sense because West Antarctica has a lot more ice cores, you can see over here, than East Antarctica, and accumulation rates are much higher in West Antarctica than in much of the interior East Antarctic plateau. So it makes sense why our reconstruction does better there. And with this, we've validated enough of our reconstruction to say, with a reasonable degree of confidence, that we have a skillful reconstruction. And so now we move on to the actual trends that our reconstruction finds. And so first, looking at the Antarctic ice sheet overall, we do find a positive, significant accumulation trend over the course of the 20th century. And you can see that this accelerates into the late century. We have about 0.4 gigatons per year squared of a accumulation rate trend from 1901 to 2000, whereas in the latter half of the century, from 1957 onwards, we have a 1.1 gigaton per year squared trend. And now we want to break this down into the regional components. And so first we look at West Antarctica. And we can see that the positive accumulation trend over Antarctica at large is dominated by the trend in West Antarctica. And to be more specific, it's this late century acceleration of increasing snowfall that's driving the positive accumulation trend. And now we come to East Antarctica, and here we find that over essentially all time periods evaluated, the trend in snow